Hi, can you give permission for me to share a screen?
Yeah, I think just try. I think I have given for everyone. Anyone can share. Uh, are you not able to?
It says we cannot start
Okay.
screen share while
Okay.
the other participants is
Oh,
sharing.
okay. Okay. 1 second. Uh, yeah. Can you try now?
Yeah, sure. Okay, now it works.
Okay. Okay.
Hi, can you give permission for me to share a screen?
I think we can start. I mean, if you are okay.
Okay, yeah, I'm ready. We can start. Yeah.
Okay. Okay. Sure.
Okay. Okay, so I will actually begin with recalling some results that we proved in the last lecture. Okay, so after that, I will try to prove two important results in this lecture. I hope I will have time. So one is primary decomposition theorem. Another one is Jordan-Chevalier decomposition theorem. Okay, so let me begin. So what we did in the last class, we were actually talking about change of basis and then how the matrix of a given linear operator with respect to some fixed basis changes when you do change of basis. Okay, so I will actually recall what we have done. So because this is very important information, okay, it's worth recalling. So let's fix some notations that we always do. Okay, so we start with finite dimensional vector space over field F. Okay, uh, so actually we will be actually talking about minimal polynomial and so on in this lecture. So if you are comfortable, you can take F to be like complex numbers. So otherwise, if you know what is algebraically closed field, so you can also take F to be algebraically closed field. Okay, so so we will just fix it to be complex numbers for time being. Okay, so we work with this finite dimensional vector space V, which has, let's say, dimension of V over this F is n, and then we will also fix a basis throughout. Okay, so we call it V bar, which is the basis that is given to be V1, etc. Vn. So this is the space that I'm working with. So what I'm interested in, I'm interested in actually understanding these linear transformations so that act on this space V. Okay, so how we so I have already motivated why we are interested in the linear transformation. Mainly we are interested in actually computations of matrices, and we can actually bring that problem to this understanding the general linear transformation. Okay, let me not get into that again. So let's say we are given actually uh, linear transformation from that is acting on this space V. So call it T. Okay. So then what we define this matrix of this T with respect to this basis V bar. So we actually denoted it by MTV bar. Okay, what is this? So this is the matrix of T with respect to this fixed basis V bar. So if suppose this matrix is actually Aij, so which is supposed to be n by n matrix. So then what are these ijth entry aij, how they are defined? They are defined using the following equation. So what is that equation? So you take this tvj, so that is actually written as, we know that linear combination of vi's. So those coefficients of vi will be the aij, I range from 1 to. Okay, so this is the equation that defines this matrix of T with respect to the basis V bar. So this is something we already saw. Okay, this is the definition. So what is the important thing that we proved in the previous lecture? So here is the fact. So let me just state the fact, because this is something we saw already. So now I want to actually take another basis, call it W bar, and then I want to compare this matrix of T with respect to these two different bases, V bar and W bar. Okay, so how I'm going to do? So suppose this A is the matrix of T with respect to V bar, and B is the matrix of T with respect to W bar. So where both this V bar and W bar both are bases. Okay, where V bar and W bar are bases of this vector space, given vector space V. So then what I want to know, I want to compare these two matrices AB. So how they are actually related? So they are related by conjugation, and the conjugation is also like given by very explicit matrix, which is the transition matrix from this basis V bar to W bar. Okay, so then what we proved? So B is equal to P inverse AP. So where this matrix P, which is given by Pij, defined to be, okay, defined as follows using this equation: Wj is equal to summation Pij Vi, I ranging from 1 to 2. So this is the equation that actually defines this matrix P. So which is called a transaction matrix. And using the transaction matrix, so we will be able to write this B in terms of E. Okay, so this is very important fact. So if you change basis, then the matrix of T with respect to those two bases will be similar. And I already told you, like if you take any invertible matrix P, it is not that hard to come up with this Wj, so that the matrix of T with respect to this W bar looks this P inverse AP. So in other words, so what we proved actually, we proved that this change of basis corresponds to the conjugation of this matrix. Okay, so this is what we understood. So this change of basis, so this is actually corresponds to this conjugation or the similarity. Okay, so that means so we don't need to like really worry about this operator. Okay, so if you are interested in actually like somewhat simplify or understand more about how this operator acts on the space, so then it is enough to find some nice basis. With respect to that, the matrix of that operator looks much more simpler. Okay, so the problem of like whatever problem that we have initially started with, which is the computation of matrices, turns out to be like in this new language, so that fundamental problem becomes this problem. So what it is, so this is the problem. So find a basis, and somewhat nice basis. Okay, V bar such that when you look at this matrix of T with respect to V bar, so this looks somewhat simpler. Okay. So that is our ultimate goal. So that is actually like why it is enough. That actually follows from this fact. So because if I change the basis, then I know that how the matrices are related. So the matrices of T with respect to two bases are how they are related, we know already. So assuming that fact, so this is the ultimate problem that we want to answer. And of course, like, so before actually getting into this hardcore problem, like first let's understand some important things. Okay. So here is the first fact in some sense, which is not that hard to prove. So I will leave it as exercise. I believe it is there in the problem sheet. So what is this exercise? Suppose if you have an operator, okay, let's say take this T to be an operator on V, and so what we are going to do, we are going to write V as some direct sum of finitely many, okay, because everything is finite dimensional, everything will be finite here. So you write V as direct sum of T invariant subspaces, okay, for some T invariant subspaces of V. So, okay, let's say V. So, let's say this is given already. So V is already given to be direct sum of T invariant subspaces. So where I choose, okay, basis for each individual subspace VI. Let's call it VI bar. So VI bar, okay. So this is the basis. So this is also given to us. Okay, we write it here. So this is already given, and then let VI bar. So this is some basis of VI for each. Right. So this is also given, let's say. So then I want to actually compare the matrix of T with respect to this new basis, which I construct for V as the disjoint union of this VI bar. Okay. So you take, so this new basis V bar, which is nothing but V1 bar, disjoint union, etc., disjoint union VK bar. So this is like putting together basis of this direct sum, so that disjoint union of that will give you basis. This is something you must know already. So this given new basis, which is formed by this disjoint union of VI bar, so that is given. So now with respect to that, I want to ask how the matrix of T with respect to this V bar looks like. Okay. So then what we can prove that the matrix of T with respect to this V bar, so this looks like a black diagonal matrix. Okay, so this is very explicitly given by, so first you take the matrix of T V1 bar, and then you take matrix of T V2 bar, and so on. And then you have matrix of T with respect to Vk. All other entries are 0. Okay, so this matrix of TV bar actually looks like block diagonal matrix. So that is the one advantage if we have such thing. So this is some simple observation. Again, we can make about general operators. So if you are able to write V as direct sum of T invariant subspaces, and then you take basis of each vi and then take union of those bases and then form a basis of capital V, then the matrix of T of this V bar will look like a black diagonal matrix with the diagonal entries of this M of T Vi bar. Okay, so this is something not that hard to prove. So this is just if you write down the action of T, then with respect to this new basis V bar, then you will know actually how it acts, and then using that you can write on this. Okay, so this is something I will leave it to you to check. So now you can actually see like so once this exercise suggests if we can write V as direct sum of T invariant subspaces, then somehow our work is simplified because we are actually looking for some simpler form of this M of T V bar with respect to some V bar. Okay, so then what we can do, so let's say suppose some 10,000 by 10,000 matrix is given. If we can write it as like matrices of block diagonal matrices, which has like 10 by 10 size, or max is 50 by 50, then what you can do, you can focus on the particular block and then try to understand that. Okay, again, this is the same as this divide and ruling policy. Okay, so the bigger problem you actually somewhat break down into smaller problems. And of course, I'm not saying that, first of all, why such decomposition exists. That is something we want to prove. Okay, so that is actually we will see that that comes from some abstract algebra. So using some knowledge about polynomial rings, we will be able to actually say this quickly for a given operator T. Okay. So one more thing, like so this is actually even writing some matrix into this a black diagonal form is not that bad, because if you are interested in computation about the matrix, then if you write matrix as A1, A2, etc., AK, so as a block diagonal matrix, so then, for example, like if you are interested in finding determinant of A, so that will be just a determinant of A1 times etc. determinant of AK. Okay, so some informations you will be able to get always from this black decomposition. So that means, so this is not bad. So if you get something like this is actually well and good. So as a first step, we should be able to get something like this. Okay, so that is what we are going to do. And that actually we get it from some applications of this understanding this polynomial algebra, FX. Okay, so like I said previously, if you are interested in finding decomposition of given space as a T invariant subspaces, first of all, you should be able to produce lots of T invariant subspaces. Okay, so one thing that we already observed, suppose you are given this operator T from V to V. So then if I take any polynomial, let's say Q of G of X from Fx, okay, so this is the set of polynomials, in one variable X. Okay, so then what we observed, if I look at this kernel of G of T, so which is those vectors in V such that G of T is actually 0. So G of T V is actually 0. Okay, so then what we observe that this is indeed is a T invariant subspace. So I'm not saying anything about whether this subspace is non-zero or not, but I'm just simply saying this is just T invariant subspace. So that means I'm able to actually able to get lots of T invariant subspaces. Okay, so of course you may wonder like why such, first of all, such non-trivial subspaces will exist. Okay, so what can happen, like if I'm looking at something like this, okay, it may happen that all of them may be zero. Okay, in that case I'm not getting anything interesting. So but I'm saying that will not happen. Can anyone tell why it will not happen?
That
So
will happen only if it is one-to-one.
sorry, if it, sorry, can you repeat again what you said?
Sir, because we have generalized eigenspaces as a ready-made example for that.
Okay, so you know already what is generalized eigenspace. So you are saying that that will be always non-zero. Is that what you want to say? But again, like this generalized eigenspace and so on, they require more knowledge about something. Okay, for example, to define generalized eigenspace, you need to at least know what is the characteristic polynomial or minimal polynomial. Okay, so let's not get into that right now. Of course, that's we will do that. But what I'm asking, much more simpler question. So what I'm trying to ask, so this kernel of g of t, it could be zero or it could be non-zero. Okay, for all g. Okay, so I'm saying, so this cannot be zero for all g of x in f of x. So this statement, okay, is not true. That's what I'm saying. So I'm asking whether can you prove this?
Sir, in the place, if this were true, then if we, in the place of gt, we can take powers of t, and which will end up proving that t is always a nilpotent matrix.
Yeah. Okay. First of all, okay. So in place of g of x, you are saying you can take powers of x. Okay. For example, you can simply take t. Okay. So like already, so you can take g of x to be x, then that means kernel t is zero. And you know, for when kernel can be zero, na? Kernel is zero if kernel of t is zero if and only if t is 1 to 1. Okay, so that means at least for this polynomial, if t is not 1 to 1, then this is not true. Kernel t must be non-zero. So what so if it is actually okay, this is one case that will be ruled out. So now you are saying you take powers like this, and then if all of them are zero or some power is zero, what do you want to take?
All powers.
If all kernels are zero, then what?
So will the matrix be nilpotent in this case? I mean, I have to check it rather.
No, that you can't conclude. Now, when something is nilpotent if some power is zero. So that means the kernel of that power will be full. Okay, t power k is zero means what? So as an operator, it is zero. So that means the kernel of t power k must be entire v. So then only you will be able to actually say this is nilpotent. But here we are looking for other extreme. Nah? Why they cannot be all of them zero? Actually, this is itself suggesting something. So sometimes the kernel of some polynomial in T could be equal to the entire space. So what is the meaning of kernel of some polynomial in T becoming the full space? So what is the meaning of this?
Null space is 0.
No, this is the null space. Kernel means for me null space. If you want to use that, you can use null of.
Then GT has to be the multiple of characteristic polynomial or minimal polynomial.
See, so far I haven't introduced what is minimal polynomial or characteristic polynomial. This, what you can say, this is from this you can simply say G of T must be 0. That's all you can say on B. Is that correct? So, okay, I will introduce what is minimal polynomial. So in terms of minimal polynomial, you can say actually minimal polynomial must divide this G of X. So that is the correct characterization. So if and only if, so I will in a minute, I will actually introduce what is the minimal polynomial. So the minimal polynomial of T divides this G of X. Okay. But my question is, I'm not actually worried about minimal polynomial or anything. I'm just worried about, does there exist polynomial such that G of T is equal to 0 on V? So that is the only question that I'm worried about. Is it possible to find some polynomial such that kernel of or null space of G of T is entire space?
Characteristic polynomial.
Yeah, so characteristic polynomial is true, but that is actually a theorem. Okay, what is that called? The theorem actually has a name.
Cayley-Hamilton.
That is Cayley-Hamilton theorem. So Cayley-Hamilton theorem actually promises you that characteristic polynomial satisfies this property. Characteristic polynomial of any operator will kill T. But my question is just, can you prove that any given operator T, there exists some polynomial such that this polynomial kills T? Okay, so let's closely look at it. Okay, so you have a polynomial algebra Fx, and then you have this endomorphism of V. So this endomorphism of V, this is some very interesting space. Okay, so this is indeed an associative algebra. So you have endomorphism of V. Once you fix the basis, you can identify with matrices. Okay, n by n matrices. So you have addition, you have scalar multiplication, you also have multiplication in this space. Okay, this space is very interesting space. Okay, in some sense, this space possesses almost all algebraic structure that we know. Okay, so this has addition, scalar multiplication, and multiplication. So multiplication is given by composition. Okay, so that makes this is an associative algebra. So now what we can do, given T, okay, this T is fixed. Okay, this is the fixed T from endomorphism of V to endomorphism of V. Now using this T, can you define this, a map from Fx to this endomorphism of V? Is there any map given this?
Evolution map.
Evaluation map, yeah. So I can take some polynomial Fx, I can simply send it to f of T. So that is a well-defined map, and that map is an actually algebra homomorphism. So it respects this addition, scalar multiplication, and multiplication that are defined on this endomorphism. So in particularly, as it is also a ring homomorphism, it is also vector space homomorphism. Okay, so in particularly, I can talk about kernel of, let me call it this phi. Okay, this phi is actually evaluation. Usually people write this EVT. Okay, so EVT means evaluation of T. So the kernel of this map, so which is those polynomials inside this algebra fx such that f of t equal to 0. So this is actually called the kernel of this map. Okay, so now what I want to say, so reinterpret the statement that we were looking at. So we were actually looking at this kernel. Nah? So here, kernel of g of t is 0 for all g of x in fx. Then in that case, what will happen? So that means, sorry. So what is the statement that we were looking at? Yeah, this statement. So yeah, so this is something like we started with, but we realized that for nilpotent operator, we will be able to get entire space as kernel of t power k. So in particularly, I asked this question, whether there exists some polynomial g of x such that g of t is 0 only. Okay, so that question, now if you reinterpret in terms of this, then what will happen? If there is no such polynomial, non-zero polynomial, then what will happen to this kernel phi? This kernel phi becomes, this kernel phi becomes 0. Okay. So, but the thing is, if kernel phi is 0, then what will happen to this map? This map will become 1-to-1 map. Is it possible to have this map 1-to-1? So what is there on the left hand side? Left hand side you have fx. So what is the dimension of fx?
Infinity.
So this is infinite dimensional space, and on the right side you have endomorphism of V, so which is actually
Finite dimensional.
finite dimensional space. So that means this kernel phi cannot be actually 0. So that means this must be non-zero. Okay, so but this kernel phi is actually an ideal inside this fx.
Principal identity.
Yeah, so we know that some information about this fx. This fx is very, very nice algebra. So it's a principal PID, integral domain. So in particularly, this kernel phi will be generated by some polynomial, call it P of x. So what is the meaning of this? This is actually P of x times f of x, where f of x is coming from fx.
And px is of least degree.
Yeah, P of x will be of least degree actually. So that is also, there are many characterizations for this of P of x. So maybe I will write down some of the characterization. Okay, that I will leave it as exercise. So this P of x, you can actually choose it to be monic polynomial because we are working over field. So if the largest that coefficient is non-zero, you can multiply by with the inverse of that and then make it monic. Okay, so by choice, what we do, we take it to be monic polynomial. So then how this monic polynomial P of x is defined? Okay, this is called the minimal polynomial of, okay, so this is actually called the minimal polynomial. So this is minimal polynomial of T. So just look at it, how we define the minimal polynomial. So you take this evaluation map from fx to this endomorphism of V. Then you can actually talk about kernel of this evaluation map. That kernel of this evaluation map will be an ideal. That ideal is generated by some unique monic polynomial. That monic polynomial, you define it to be minimal polynomial of T. And most of the time in books, actually, they give all the characterization of this minimal polynomial. So for example, the following statements are equivalent. Okay, suppose f of t is 0, then that would imply p of x divides f of x, and p of x, okay, let's say I have already fixed the monic, okay, p of x monic polynomial such that minimal, maybe I should write it like this. P of x is the minimal degree non-zero polynomial such that whenever f of t is 0 should imply p of x divides f of x. Okay, so this is the characterization. Actually, like, yeah, this is the only characterization. Or otherwise, so another, okay, maybe if you, the way I defined it is already chosen that way. So other way to define is take this kernel of this evaluation t, and that is generated by this p of x, which is monic. Okay, so these two are equivalent. So now what is Cayley-Hamilton theorem says? Cayley-Hamilton theorem says this characteristic polynomial of an operator that is actually belongs to this kernel. Okay, so this is Cayley-Hamilton theorem. So which I will prove, but I will actually like prove using some other method. So let's state the theorem. Okay, Cayley-Hamilton theorem says if you take the characteristic polynomial, which I denoted by chi t of x. So what is the definition of characteristic polynomial? It is determinant of a minus x identity. Okay, so this polynomial is divided by this p of x. Okay, this is Cayley-Hamilton theorem. Okay, we'll come back to this later. Okay, let's not worry about it. So we have defined what is minimal polynomial. Okay, so now what we are going to do, we are going to use this minimal polynomial. So to define minimal polynomial, I don't need to know what is characteristic polynomial and so on. Okay, I can use the evaluation map and then define the minimal polynomial. So now once I know what is minimal polynomial, then I can actually prove the primary decomposition theorem. Okay, so I will just do that now. So now what you can do, like if you take your field to be algebraically closed field, okay, but if you are not in algebraically closed field, then there is something called extending scalars. Okay, so let's not get into that right now because that's much more confusing. So you can assume your field to be complex numbers for time being. Then if you have this complex numbers, then you know that any polynomial can be factored into a product of linear factors. So in particularly, I can write the minimal polynomial of this operator t as some x minus lambda 1 power a1, etc., x minus lambda, let's say, r power ar. Okay, so where these lambda i's are all distinct, where these lambda i's are distinct roots of this p of x with multiplicity ai, which is greater than equal to. Okay, so I'm counting this lambda I with multiplicity A. So now this allows us to define what is this generalized eigenspace. So you take this Vi, which is the kernel of this T minus lambda I identity power A. So this is your generalized eigenspace. Corresponding to lambda. Okay. So once you know this generalized eigenspace, then now it's not that hard to actually write down the decomposition. So here is the primary decomposition. So why it's called primary, it's very important. And as well as this is the first decomposition theorem that you are seeing for general operators. Okay. So what is this theorem says? So V can be written as this V1 direction, etc. direction PR. So where VI's are given by this. Okay. So note that because these VI's are nothing but kernel of some polynomial in T, so all of them are T invariant subspaces. Okay, each Vi, they are T invariant subspaces. So now because they are all T invariant subspaces, you can actually take a basis of each Vi and then put them together to get basis of V. So with respect to that, you can actually write a matrix of T with respect to that basis as a block diagonal matrix. Okay, so this is something promised in this exercise that you can do. So like this. So this is like this you can do. Okay. So the proof of this is not that hard actually. So this just uses that some polynomials are relatively prime. So you should know some information about relatively prime polynomials. Okay. So given this factorization of P of X, so we should be able to actually come up with some set of relatively prime polynomials. Just play around with that. Then we will be able to prove this decomposition theorem. So let's do this. So this is a very, very important proof. Okay. So I have actually indicated what is really going on in the problem sheet. Okay. So that there I have actually done it for only two polynomials, which are given to be relatively prime. So here there are given relatively prime polynomials. You can actually deal with this directly. So if you are interested in that another proof, how it actually goes, you can actually do that two polynomials first, and then iteratively you can actually come up with this proof of this. Okay, so more or less both proofs are same. So now to prove this, so there are two statements. Okay, if you are interested in proving something like this, so first what you need to prove, you need to prove that this V is actually sum of these subspaces. Okay, so this is the first thing. And the second thing, and to prove is actually, so these VI's are in some sense independent. Okay, so that means if I take any linear relation, okay, which is coming from this vectors of Vi, such that this sum of these are 0, okay, for some Vi and capital Vi, that should imply me each Vi equal to 0 for all. Okay, so these two is equivalent saying that V is direct sum of this V1 etc. V. Okay, so let's prove. I will prove this first one, and then maybe second one I will leave it as exercise. It's not that hard to prove. Okay, so to prove first one, we want to write V as given. Okay, let's fix V in V. We want to write given V in V as sum of vectors from this capital V. Okay, So the only information that is given is the minimal polynomial. Okay, some books write it as minimum of x t. So it is the d minimal polynomial. So this is given to be x minus lambda 1 power a1, etc. x minus lambda r power a. So this is something given. Okay, now let's use this information to write v as sum of vi's. Okay, how I can write? Okay, so to do this, the trick is from this one polynomial, I want to produce r number of relatively prime polynomials. Of course, not something random, which actually does the job. So first of all, can you give me r relatively prime polynomials? Anyone from this information? Only from this information.
You can add 1 to this one.
You can add 1. No, this is the product. X minus lambda 1 power a1, etc. X minus. Sorry. So, like if you know the factorization, okay, let's say I have given you two polynomials. We can call it fx and gx. Okay. So when they will be relatively prime, assuming that you know the factorization, how they factorize.
Their GCD will be 1, sir.
Yeah, so their GCD is 1. So that is the definition of relatively prime. But assuming that you know the factors.
The powers are 1. Should be linear factors. Linear factors. This is AI. So these are because we get the minimum of the powers, that is the GCD.
No, let's say I'm giving you two polynomial, okay, f of x, g of x.
No common factors.
No common factors, exactly. They should not have common factors. If the factorization is like this, and then if the factorization is like this, then none of this lambda I should be equal to none of this mu j's. Okay, so then only they will be relatively prime. So now what I have given you here is actually this is the data I'm giving you. These lambda is are distinct. That is the data. From that, can you give me r number of relatively prime polynomials?
First is x minus lambda e raised
Yes,
to
sir.
pi.
We can take polynomial.
We can
Each factor
omit
is
every
there.
step.
Just
Okay, we
separate
can
all
simply
the powers.
take
Each
someone
factor
said,
at a time.
yeah, x minus lambda I. For example, we can take any power of them, doesn't matter. Here the powers are fixed. Let's take this. If I take these polynomials, okay, are they relatively prime?
Yes, sir.
They are relatively prime. Yeah, very good. So, but now what I'm interested in, I am interested in writing given, okay, go back to the original thing. I want to, given vector v, I want to write down this vector v as v1 plus etc. some vr. This is how I want to write down. So this is what I want to prove. Huh? But what is the condition? Condition is this v1 should be inside capital V1, which is kernel of t minus lambda 1 identity power a1. So that means this t minus lambda I identity power ai should kill this va. So this is what we want. Okay. Somehow this va should be killed by this. I also want to come up with this va. Okay, but I want to use this information. So I want to come up with other set of or relatively prime polynomials. When I use that information, I will be able to get something like this. Can you guess some other relatively prime polynomials? So the one that I have started with, if I take, that will not do me the job actually, because so what is the one that I have taken? X minus lambda I power ai. If I take this, then I will be getting some gi of x, such that when you sum it over this, we will be getting 1. Okay. So if I use the evaluation, then what I will get summation I ranging from 1 to r gi of t minus lambda I identity power ai equal to t. So this is by applying the evaluation map. Okay, apply this evaluation t, we get this. Sorry, this is identity. Now using this, what I can do, I can write v as summation gi of t minus lambda is identity v power aiv. Okay, I range from 1 to r. So I can write v as sum of this. But the problem is this one, okay, some of this is something, if I want to call it vi, it should be killed by this t minus lambda I power ai. But that is not the case here. Okay, so that means this is not the correct choice. But if I want it to be killed, then I need to take something else here. What should I take? That is the question. What I know P of TV is 0. Do we know this? Because P of T is nothing but the minimal polynomial of T. So that means if I take T minus lambda 1 identity power A1, etc., T minus lambda R identity power AR, applied on V is 0. So this is something I know. Okay, so that means from this factorization, I can each time I can start ignoring one factor and then look at the remaining things. Okay, and that should be my polynomials. Okay, so what I can take fi of x, so define this to be just ignore only that ith factor, x minus lambda j power aj, where j is not equal to I. So f1 of x, I ignore x minus lambda 1. f2 of x, I ignore x minus lambda 2, and so on. Then I leave it as exercise. It's not very hard to prove this fi of x, okay, or relatively prime. Why? If they are not relatively prime, it must have some common factor, and it must have one common linear factor, but it is not that hard to see they cannot have common factor, because every time you are ignoring one factor. Okay, so then it must be relatively prime. So in particularly, I can write for some hi of x, summation hi of x, fi of x is equal to 1 for some hi of x. So now again, go back to the trick. So this means if I apply again evaluation, this will give me hi of t, fi of t, v equal to v. I range from 1. But look at this.
Sir, I have one question. How these FIs are relatively prime?
So FIs are how they are defined. FIs are defined to be you ignore the ith factor, na? X minus lambda I.
Yes.
Remaining thing you keep. Okay, for example, let's say.
But sir, for example, if I take F1 and F2, so we are ignoring first and second factor respectively, right?
Yeah,
But
yeah.
others factor will be common, no?
To
So
find all the
F1 and F2.
No, but I am taking all of them, na? F1 up to F4. All of them are related prime, not mutually related prime.
Okay, okay. So, you are saying F1 to Fn.
Yes.
So you are taking
Yeah,
all
yeah.
of them together. And
All of them
then they-
together
okay.
are related.
Yes, yes. Okay. I thought they are mutually okay.
No, 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 no. I don't. I
Okay.
only want this.
Okay, fine. Yes, sir.
For this, I need only like yeah. So all of like okay. I should put one listener equal time, listener equal time. Not mutually. They are actually all of
Okay,
them.
understood, sir.
Yeah, together related. Okay, now you have this. So now I can simply take Vi to be Hi of T, Fi of TV. So that means if I take T minus lambda I identity power AIV I, then you can see that it will be Hi T P of TV, which is 0. So that will imply that Vi is in the kernel of T minus lambda I power A. Okay. And this implies V can be written as V1 plus etc. Vr with Vi is in this Va, capital V. Okay. This proves this, the first statement that we wanted. This statement. Okay, so this is just playing with suitable polynomials. So for the second statement, what you need to do, you need to take, for example, if you have a relation like this, V1 plus etc. plus Vr equal to 0. So for example, you write V1 equal to minus V2 plus etc. plus Vr. And then take these two polynomials, x minus lambda 1 power A1 and F1 of x. So these two are relatively prime because the common factors are like there is no common factor. This one doesn't have that x minus lambda 1 power a. What is this? This is nothing but x minus lambda 2 power a2, etc. X minus lambda r power a. Okay, now using these two are relatively prime, use this to conclude V1 is 0. Okay, and similarly you can conclude V2 and so on, everything is 0. So I will leave it to you to check this because proof is same, ditto, there is no difference. Okay, and that proves actually that V can be written as V1 direct sum etc. direct sum VR with so where okay this Vi is nothing but kernel of T minus lambda I power A. Okay, so this is what. And there are many interesting corollaries. Okay, for this theorem, I will actually state only one corollary, which is very important. That gives actually characterization of diagonalizable matrices. Okay, so as a corollary, you can see that. So what is diagonalizable matrices? Does anybody know?
Similar to diagonal matrix.
Yeah, they are similar to diagonal matrices. Okay, so if an operator is diagonalizable, by definition, there exists some basis such that the matrix of that operator with respect to that basis looks diagonal. Yeah. So then in that case, we call it actually this T is diagonal. Okay, diagonalizable. Sorry, diagonalizable. If there exists V bar such that this happens. So now what one can prove, if T is diagonalizable, okay, if and only if so now look at this decomposition here. So when this will actually become diagonal matrix, when we will get this, you already know the answer. Actually, you have a generalized eigenspace, okay. So when you have a diagonal matrix or diagonalizable operator, then the generalized eigenspace will become what?
Dimension 1.
Not dimension 1.
Base for a V.
The multiplicity that AIs becomes 1, okay. So it becomes eigenspace. Generalized eigenspace will come down to eigenspace, okay. So you can see that T is diagonalizable if and only if AIs are 1 for each I. If and only if the minimal polynomial factors into linear factors. Okay. So linear means distinct, of course. So then only I can say T is diagonal. So it's a very important corollary that comes for free. Okay. And that is obvious now, because if AIs are 1, then what will become? VI becomes kernel of T minus lambda I identity. Okay. That means T acts as lambda I on that subspace. Okay. So that is the eigenspace. So then you can prove that the matrix of T with respect to that V bar will look like lambda 1, etc., lambda 1, like this, lambda 2, etc., lambda 2, like this. Okay. So this is actually the diagonal matrix corresponding. So the eigenspace may have more dimension, okay, but it will corresponds to one eigenvalue. Okay. And again, like there are many interesting corollaries you can actually prove using this. For example, if you start with an operator and then some subspace which is T invariant, so then what you can prove, T restricted to W, so which is an element inside this endomorphism of W. Huh? So this is actually, again, if T is diagonalizable, okay, this is diagonalizable, let's say, then this is also diagonalizable. This is also you can prove. Okay, so that is again like follows from that minimal polynomial of this T restriction W will actually will be divided by the minimal polynomial of sorry, the other way. So the minimal polynomial of T restriction W will divide the minimal polynomial of T. So the minimal polynomial of T restriction W divides the minimal polynomial of T. Okay, so just this is okay. Anyway, I'm running out of time, so we will see some more applications of this primary decomposition theorem maybe next class. Okay, I wanted to actually finish this Jordan-Chevalier decomposition, but anyway, it's already time. So there is one very important consequence of this primary decomposition theorem. It's yeah, most fundamental theorem that you learn about canonical forms. Okay, so so there is some additive decomposition of any given operator. Okay, which is called Jordan-Chevalier decomposition theorem. Okay, so that is something I will prove next class. Chevalier decomposition. So what it says, actually any operator, okay, can be written as some diagonalizable operator plus some nilpotent operator. Okay, satisfying some specific properties. Okay, so that is called this Jordan-Chevalier decomposition. So once you assume those specific properties are satisfied, then this decomposition will be unique. Okay, so this is something you can prove as a consequence of this primary decomposition theorem. So now, once you write something like this, then what happens? The problem of understanding this any operator will come down to the problem of understanding only this nilpotent operator, because this diagonalizable operator you understand very well. So they are nothing but diagonal matrices, okay, corresponding to some sorry, with respect to some basis. And so in this decomposition, both this S and N, they mutually commute. So you will have a basis with respect to that. Both this S and N will be like simultaneously written in some form. Okay, S can be written in diagonal form and N can be written in some nilpotent form. Okay, so then if you are interested in coming up with any simpler form for T, then this Jordan-Chevalier decomposition will allow you to only focus on this nilpotent part. Okay, so we will come to this later, maybe tomorrow. I will stop here. Yeah. Do you have any questions?
Okay, thank you, Venkatesh. I think if there are no questions, we will take a quick, I think 4 minutes break, and we will start at 7:10 exactly.
Okay, yeah, I will stop sharing. Thanks.
Oh, okay. One of the Vipul has asked that can we get the PDF of the running notes? Yeah, I think Venkatesh will share it with me, and I will forward it.
Yeah, I already shared that last.
Yeah, that I have uploaded. I think the.
This one I will actually share it.
Okay.
Share it today or tomorrow. Yeah. Sure.
Okay. Okay.
Is it a new file or the same file?
I think. Yeah.
Is it a new file or the same file I asked?
No, this lecture I am writing as a new lecture notes.
Okay. Okay.
So yeah, that one has some informations about primary decomposition theorem, but
okay,
but it's okay. Like I'm repeating it again. Not a problem.
And I think there's also a question from Vipul that any books, any suggestions for books to study, I think this kind of primary decomposition and such thing.
So yeah, primary decomposition theorem actually it is done in all standard books. Okay, even yeah, all books actually does primary decomposition theorem, but I don't think this Jordan-Chevalier decomposition, this additive version is there any of the linear algebra books. Manjunath, do you know any book?
No, actually, in fact, Husstein does all these things, is it? I mean, I'm not sure. I never used that, so I don't know. What is the Jordan-Chevalier?
Yeah, this is additive version. Usually they write the multiplicative version.
No, really, I don't know.
This is writing an operator as diagonalizable plus nilpotent operator. Then the reducing this problem of cyclic decomposition to the nilpotent operators.
I see. Okay.
So maybe I will try to write up some notes and then make PDF file. But I don't promise it to do it immediately. But maybe after a week or 10 days, I will send it.
If you let us see a reference, just send a mail to Sushoman. You can share it with all the.
Okay, sure. Oh, I forgot there is this Russian author notes I have learned it from actually. But this Jordan Chevrolet decomposition is there in any real books actually.
I see, I see. So you're in Chennai now, or what? I mean, you're doing from Chennai, or
Me, I am in Bangalore only.
oh, you are here? Okay, okay. Yes.
Yeah, we got COVID last week, all of us.
Oh, I see. Oh, okay. How are you?
Yeah, we are fine. Kids are having, all of us having cold still. Already 5-6 days.
I see, I see.
Kids have been having more than 10 days.
Oh,
I got first 3 days lots of body pain.
yeah, yeah.
Same body pain. 3 days was there. Then yeah, fine.
Oh, I
But
see.
cold is still there. I don't know how many.
Yeah.
I'm not taking any medication, but I hope it.
For me also similar. Cold and cough stayed for long, but
Okay.
got beginning then.
Body pain, like I remember this chikungunya came na sometime.
Yeah.
That time, whatever body pain I got, very similar body pain.
I see.
Okay, it's almost time. Should we start? Sir, Nandakumaran sir, should we start then?
Yeah, I'm fine unless they need a rest another 5 minutes. Otherwise, I am fine. I'm ready.
Yeah, everyone participants, should we begin, or should we take some 2-3 more minutes of
Yes,
rest?
we can start, sir.
Yeah, I think we can. There, everyone is ready. We can start.
Okay, then. Good evening to everybody. Can you hear me?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so I'm using another joining through two computers to avoid my trouble last week. Let's see whether I will be successful. I'm sharing through. Is that visible?
Yes, sir.
My screen is visible?
Yes, sir. It's visible.
Okay, so this may be lecture number 4, right? All right. So today we will do the derivative of vector fields. Since we have done all the groundwork for the scalar field, this is now quite easy. Derivative of vector fields. So what is it? You have an f now from omega to omega Rn to Rn. You can do that. So you have your Fi, if you want to be, it's from omega to R. This is a scalar field. So you can give the same definition of derivative, the first thing, derivative along a direction. Only thing is that it's vector. So careful while dealing with it. Derivative of f at a, the direction y. Direction. Where a is in Rn, y is also in Rn. It's the same thing. So same notation I use it. I don't change the notation. F prime of a y is equal to limit h tends to 0 of f of a plus hy minus f of a by h. Note that this is a vector. This is a vector. Everything is in vector. Earlier it was scalar. Of course, this can write it in a fk form also. So whenever the limit exists, we say that the derivative of a, this is the derivative in the direction. So this can be write it in a maybe slightly in a compact notation if you want. K equal to 1 to m. This is up to m. I equal to 1 to m. Okay. So this is nothing but your fk prime ay into ek tilde, right? You can write any vector in terms of where ek tilde is the canon. So I am separating ek tilde, which is the canonical basis, is k equal to 1 to m basis, canonical basis in Rn. Yeah. So ek I use it as the basis in Rn. Okay. So you do that. So that's a similar definitions what we have given. Now we can give the general definition of the total derivative. Total derivative. Again, the definition is similar. Only thing that linear transformation, you have to take it at the right thing. I'll go a little faster than in the last couple of lectures. We say F is, because we had elaborately done in the case of scalar field to get you everything. F is differentiable, Fresher differentiable or dot differentiable at A if there exists a linear operator or linear transformation TA from Rn to Rn. Keep that now, it's Rn to Rm. Okay. Such that exactly the definition similar, f of a plus v for v sufficient as v tends to 0 basically. Fa plus Ta of v plus v into Ea of v, where Ea of v goes to 0 as v tends to 0. This is equivalently, in some books will write it as, is equivalently writing that one is limit existence of Ta, limit v is a vector now. Keep that in mind. So when I say that v tends to 0, no v tends to 0. Norm of f of a plus v minus f of a minus Ta of v by norm v is equal to 0. Okay, so this is the definition. Now you look at it, remark, this definition can be easily, though we don't do it, remark, this definition can be extended to normed linear spaces. See? And where you have plenty of examples, plenty of applications. Not that you don't have applications in Rn, but then moment you generalize this process to infinite dimension, because many of the physical problems are formed in infinite dimension. All the function spaces are all infinite dimensional spaces. And you in a non-linear space, and there is a very rich theory of linear operator, but your certain metrics, etc. in the other lectures are the finite dimensional thing. So you have an infinite dimension of kind of linear algebra, essentially the function analysis. Okay, definition can be extended to normal linear spaces. I will not do that one, but I want you to give a computational example for you. You do, so it's not, you don't have to worry anything about it. A simple example. This is the famous what is called the Poincare function. You don't worry about the terminologies. I just asked you to compute. How do you compute? So you define J of U is equal to half of, this is some sort of an energy. In applications, this will be some energy. This is omega. Now the function is, J is not defined in omega. Okay, J is defined in a functional space. If you want, you can take U to be C1 function, and if you want, assume the boundary values are 0. All that, these are all C1 functions continuously. So you see J is acting here. Okay, I want you to somehow understand this one. Since I have not given any computation, so I want to understand some J prime of U. I'm not, as I said, I am not defined by above definition. There has to be a linear approximation. So there should be a linear functional now. Okay. Which gives you an approximation in the sense of no. So you don't have to worry. So basically, I want you to compute J prime of U acting at V for that. So the exercise is much more simpler. What I want you to do, it's a simple computation to this computation. Okay. J of, so U V belongs to C1 of omega, and you compute this. This is how you do your first step of computation, some crude way of doing it, right? If you want to get a Taylor series expansion, what do? You perturb it and then find the quotient and the limit. J of U by T as T10 limit, if X is. That's excellent. This is a straightforward computation. You don't have to worry, it's very complicated. Write down this J of U plus TV, which is a known, or integral something, and it's, you can expand it and compute it, and so it's a two-step thing. But what I just want to know that J of U is one of the important functionals from the last century, which is also associated with certain energy in certain applications. Okay. So I will not do that one. Okay, so this is just to indicate that you have plenty of applications which you can do it. Okay. So in the similar result, which we have proved it for scalar valued functions, if T exists, the similar thing. But what I would suggest you is that even if it is similar, try to do it and follow it analogously, what you have done for the scalar field. If T exists, then f prime of ay exists. This is what we have proved for the scalar field. And then in the scalar case, you have seen that this is gradient. That is how you motivated the gradient exists. And then this is nothing but the action of the gradient. Okay, that's okay. And then we can also do it what will happen here. So so this you can prove it. In fact, it's exactly the similar proof. So TA of y, assuming that now TA exists, then it is f prime of a of y. And that's, we are already given a notation fk of ay in terms of the component. You can write it ek tilde k equal to 1 to m, and then this is scalar field, and you have that formula already, scalar field. I'm using that, right? And so that is nothing but sigma 1 to m for G. This is nothing but the gradient of fk at a y at ek tilde. So if you want it in an expanded notation, this is nothing but gradient of f1. So the first component, gradient of f1 a dot y, etc. Gradient of fm Now look at it. Each one is a dot product. How do you get a dot product in a matrix form? You represent, if you want to get this one, this is nothing but the action of your first row in a matrix multiplication with a vector. So you can write that it as instead of that, I can write it as a row vector now. So you write it as a row vector. This is gradient of F1 at A. So you are writing it as a row vector. That's a matrix. It's also a kind of motivation for your natural things. The matrix multiplication of a matrix with a row column. Okay. And then this is now a vector. This is a scalar with action. So I'm writing it in a matrix form. M at A. And then acting at Y. Y is a vector. Y is a vector in Rn. So you have this in this direction. This is M. So this is a M by N matrix. What is that M by N matrix? That matrix is denoted by DF at A by. So what is DF where DF at A is this matrix. So grade F1. What is grade F1? df1 by dx1, right? At A, the partial derivative, and then you will have df1 by dxn at A. Like that, here you have, if you come dfm A by dx1, and then here you have dfm by dxn at A. Okay. So you see, instead of the gradient for each row corresponding to the scalar field, you got that gradient, you put it together, you got a matrix, and this is, and that's natural, and that's a matrix representation of your linear operator. And this DFA, so it's a matrix representation corresponding to DXA, is called the Jacobian. So you can work out many examples now. Exactly in the last exercise, our TS worked out for the gradient, some of the nice way of doing it. Okay, is called the Jacobian matrix. So this representation is with the assumption that it is the total derivative exists. As I said, this converse is not true. Okay, so it's a similar thing. It's exactly similar to that one. So now is a similar results are certainly proved for scalar field. You can prove that if F is differentiable at A, implies F is continuous at A. But I request or suggest all of you do these exercises, even though it follows along the similar lines. So treating these are all vectors. Okay, and you can also have your chain rule. As I said, chain rule is always important. Okay, chain rule, integration by parts are all crucial things like that. So chain rule is similar. So you have a mapping S here, maybe an open set in Rn. Okay, and that is going to a set in Rn. So you have your some other set here V, and this is in Rm, and you have a mapping to R, maybe K or K, and you have an F here, and you need the conditions so that this goes inside, so that you can define appropriately. That means V contains G of S. Okay, so you make assumptions appropriate. So you have a starting with a point here, A, and that A goes to here, that is equal to G of B. So you need the G of A. Okay, so you assume all that. So assume G is differentiable at A, F is differentiable at B. We have defined the chain rule for the scalar field, and in fact, we have seen it. Okay. And of course, what is B? B is equal to G of A. Okay. With corresponding derivatives G prime and F prime, and then that implies G composition F. It is G composition F, right? So you get the map G or F composition G, F composition G, because I had taken F second. Okay. F composition G is differentiable at A, and what is its derivative? F composition G prime at A. So all linear transformation, then F derivative at B composition. These are linear operations. G composition. These are all linear operators. Keep in mind that recall G prime A is a linear operator from Rn to Rm, and F prime of B is a linear operator from Rm to Rm2. Okay. So F prime of G, this is a linear operator from Rn to Rk, satisfying the corresponding linear equations. You can write this in terms of matrix. So let me use it in terms of matrix if you want it. In terms of matrix representation, if A is equal to dg of A, it's metric Jacobian, and B is equal to df at B, the corresponding Jacobian at B, then what it says that, you see how again a kind of a motivation for your matrix multiplication, because composition is again one of the important operations in maths. The moment you study function spaces, functions, right? After doing that, immediately you try to understand composition. So the corresponding composition, what would be the matrix corresponding matrix to the composition, the derivative of the composition is nothing but your matrix multiplication, which you are familiar. df, decomposition of f composition G at A is nothing but Bn. Okay. In other words, if you want in terms of the element, and you can write it as Ji is nothing but summation df at B J, so Jk into dg at A Ki, and K runs from 1 to M. So you see, so you have all this data, ij the element is writing. So this is same, okay. So it's nothing but if you want it in terms of the partial derivative, this is dfj by dyk evaluated at B into dgk by dxi evaluated at A, and where k running from 1 to m. So this is what your decomposition element. So you have all what you study quite sometimes in a not so rigorous fashion, and this is exactly what the representations you get it. There, as I said, just like in scalar field, I did not go to applications and many other properties because of the limited time. So now we want to go to the importer because it's already in the thing. So I want to reach a somewhat a reasonable proof I want to give. So I want to go to what is called the inverse function theorem, because there are other things to be proved there. Let's see whether how much I can do it today. Okay, so let me go to inverse function theorem, the one which we were waiting for the last few days. Inverse function. We already motivated. In some sense, we have also explained to you. So whenever you state a theorem, make sure that what are your assumptions and what are your settings. So you have a few things to understand when you write a theorem, when you read a theorem, and you understand the theorem. First, you see the settings. What are the notations you are using it? It's important to use right notations. You cannot explain something in one notation and write the theorem in another notation. Nothing wrong, but it is better to follow a unified notation when you are studying it. And then what are the assumptions given, and then what are the conclusions. So let me start with this one, inverse function theorem. Okay, so let E, can use omega, nothing wrong, open. Okay, and maybe I will use omega. E, I will reserve it for the implicit function theorem. Open, and f from omega to r. Omega to r. So satisfies, these are the assumptions which I'm going to make. Okay. Okay, assumptions. There are two assumptions. Let me also set the thing. A is in omega and B is equal to f of A. So the first assumption is f is in, I will explain this little bit. You have to understand a bit properly, not that probably you have already understood. F is C1 of E. That is f prime of x, so omega, f prime of x exists for all x in omega. Okay. And when I say that C1, f prime x for fixed x is a linear transformation. You have continuity, that's no issue. I'm not talking about the continuity of derivative. You have to have the derivative as a function of x. So that's a thing of C1. And x going to, this is the point I'm trying to say, f prime of x. And this is a mapping from omega going to f prime of x is a linear transformation. So it's a linear transformation which has a topology, which you probably already understood. L1 of Rn to Rn. Sorry, not L1. L, there is nothing here. The L of Rn to Rn. And this map is continuous. That's what I am talking. That's what you have to understand. It's not that you are talking about the continuity of f prime of x. X going to f prime of x as a mapping from omega to L of Rn, because L of Rn is also a non-linear space and it has a topology. It is a norm. So it's a non-linear space. With respect to that, this mapping is continuous. That's the one assumption. And the second assumption is the matrix. I will use the same notation as f prime of A. Okay, the matrix corresponding to f prime of A is invertible. Okay, so that's the two assumptions. One is it's about the smoothness of the function and its derivative. And the second one is infinite. That is determinant of f prime of A not equal to 0. Okay, then that's the conclusions. So let me come conclusion. Then there exist open sets okay, U, B in Rn, where it's an open set containing A and open set containing B. B is equal to f of A. Okay. Such that, what are the things it should satisfy? Such that now one, f restricted to U to V is 1, 1 on 2. And 2, once it is 1, 1 on 2, you can define its inverse. G is equal to F inverse from V to U. How do you define your inverse? Because every element is in V is given as f of x. G of f of x equal to x for all x in U. That's the meaning of inverse, right? U is also a C1 map. Is a C1 map. So you can solve it. It's not only that it's a, you can find neighborhoods and the inverse retains the smoothness of your function. Okay, that is G is in C1 of V. And you also have the exactly computation what is G prime at B. Now, G prime of B is nothing but f prime of A, which is invertible, and it is inverse is given by that. So it's very easy to understand. It's not a thing. So you have your map here. You have your A here. This is your R. This is your F. And this is your V. Not that V. This is in R. So Rn. This is your omega subset of Rn. This is your A. And this is your B. But it says that there is a neighborhood U. There is a neighborhood V. And then when you restrict this to F, this is 1, 1 on 2. And you can hence it can define F inverse equal to G. That means for every Y in this neighborhood, you have an X here. You see, and this X can be equal to this way. It's all in the inverse function theorem. Okay. Okay. So we may try to give a proof. Before giving a proof, so before coming to the proof, I need the main, and as I said, in the immediate important thing is the contraction theorem. Banach contraction theorem. contraction theorem on fixed points. So I will quickly recall it. This is a fixed point theorem appears a lot. There are hundreds of varieties of various fixed point theorem with various conditions, because certain conditions may not work to apply your applications. So if you will have, you can formulate many of your problems as fixed point theorem, fixed points, finding fixed point of the map. So what is a fixed point? Suppose V is a mapping. So let me call it heuristic, but you can define any self map from X to X. We are in Rn only. X, if X is called a fixed point, if phi of X equal to X. Since we don't have that kind of time, I don't think I can give too many examples. I have too many. There are so many. It's not limited to some few things. There are plenty of different varieties of fixed point and used to prove many. In fact, many of your problems, integral equations, differential equations, other algebraic equations, you can put it as fixed point theorem. Yeah. So for example, you can say, suppose it's a very nice exercise. You can say, suppose f is from 0, 1 to 0, 1. Continuous. Then there exists a fixed point. It's a very special case of the theorem which I'm going to state. But here you don't need conditions, okay? The theorem is more stringent. The theorem what I'm going to state is a very, very general theorem. Only the condition is stringent. So to apply that, you have to satisfy that condition. Otherwise, it's one of the beautiful, easy, the proof is quite easy. The moment you, and it's very general for a general metric space. You don't even need non-linear, much more you can do it. This is geometrically, I would like you to prove as an exercise if you want. I'm sure you would have seen it by intermediate value theorem. But that's a very easy. So if you have a 0, you have a 0, 1, fixed point means it cuts here. So if you have a mapping here, any mapping, it just tells that it is, it will intersect. It's not true, in general, not true if f is from open set. You see, 0, 1, 2, 0, 1. That's not true, right? May not be true. For example, you can find many examples. So I don't want to show, I don't want to prove. So you can construct such examples. So, okay, so the fixed point you can do that way. So what's the theorem I want to, so I want one more definition. Maybe I will write it in the theorem itself, theorem. Phi from, I'm stating in Rn, but I'm telling you it's not a must. You can replace by complete metric space. You can write down the same theorem with the complete metric space. Okay. So no property of Rn is required, but completeness is important. That's what you have seen there. If there is no completeness, the result will not be true. Okay. Be a contraction map. Be a contraction. Actually, some books may write it as a strict contraction. So, but look at the definition. Some people don't use it, contraction itself, what I'm writing. So whenever you are reading any book, make you sure that what's the definition of the contraction. Okay, sometimes strict contraction is something like when you say the monotonically increasing, some books write strictly monotonic increasing and all that. So the understanding the definition is important. So what is the meaning of contraction? I'm writing the meaning is that is there exists an alpha, there exists 0 less than. This strict one is important, such that modulus of phi of x minus phi of y is less than or equal to alpha into mod x minus y. In the case of metric spaces, just replace that phi x phi y by d of phi x phi y less than or equal to alpha into mod x. So absolutely no difference in the proof or anything. Okay, so that's assumption. So it's a contraction map. Contraction, you can see that when you are taking 2 points, when you apply phi, it becomes closer. That's what it's exact. So leading to a fixed point. That's the whole thing. Okay, this is true for all x, y in. Then phi has a unique. Then phi has a unique fixed point. Unique fixed point. That is, there exists x in such that x equal to x. The results are not always true. For example, if I take phi from phi x equal to x plus 1, translation has no fixed point. Translation. Phi from R to R. You see? Phi has no fixed point. Right? It's trivial, right? If x plus 1 is equal to x, then 1 is 0. No fixed point. But you see, what is phi x minus phi y? Phi x minus phi y is exactly equal to modulus of x minus y. So here alpha is equal to 1. So alpha strictly less than 1 is a very, very important and crucial thing in the proof of fixed point. So you're just proving phi x minus phi y less than 1, that is not enough. Okay, you have to have less than or equal to alpha into mod x minus y with alpha strictly 1. Less than. So you need that kind of uniformity and strict less than 1. It's important to have that one. Okay. The interesting thing is that though I don't give the proof steps are very easy and very computational. And you don't have to see many of the things in computation. Where do you start your iteration? If you want to do a computation, you have to start something. The advantage of fixed point is that this contraction fixed point. So the condition of contraction is stringent. Many of your applications may not apply problems, may not satisfy that. But once it is satisfied, don't have to worry anything. Wherever you start, it will lead to that one. So start with anything, step. Okay, step. Start any x naught. Any x naught. And define your xn plus 1. The iteration is nothing but a phi of xn. Okay. Show that xn is Cauchy. That's all. Show that xn is Cauchy. That's all you have to do it. And that's not difficult to show, because if you want to show that phi xn, you take a xn is Cauchy, you have to compute your that's what I say, d of any metric, you have to compute your you can compute all these quantities. Keep on doing, yeah, no, not that way. You have to compute your d of xn, xn, right? N and m large. You have to compute this. That's all you have to do. So you do step by step. When you say, for example, first compute the of xn plus 1 xn. Then by a contraction, you know that this is less than or equal to alpha into d of xn minus 1. You see? And then you can apply it again. And that will bring one more alpha, and it becoming alpha less than alpha square. You get xn minus 2, xn minus 1, you get xn minus 1. If you proceed it, end of it, you get it some alpha power n minus 1 into d of xn thing. And then add everything together, you can see that it's a kind of a tail of a series, convergent series, and you can easily prove that it is. So x0 doesn't play a role. Of course, where how you reach faster, it may play a role, but end of it, it doesn't matter. So you can prove that thing. So this is one result which we will prove in the proof of your theorem. I don't know, I can complete it, but let me start the proof of inverse function theorem. Let's do at least a major part of it. Proof of, at least if not the second part, at least I want to prove the first part. What is a theorem? Let me, okay. So you have two parts, it's a 1, 1, and 2. So I want to cook up my u and v, and then this is little more easier. There are a few steps are required for the second part, but the first part is more important to do that. Okay. So as I said, it's the fixed point theorem is true for any metric space, in particular, it's any compact set. So the theorem can be applied. Okay. Theorem can be applied. You don't need Rn nothing. Theorem can be applied. If is a K to K compact set, contraction implies contraction. It should be a self map on a compact set. That's why it's got a fixed point from 0, 1 to 0, 1. It's a self map. Okay. But there you don't need a contraction. Any 0, 1 to 0, 1, you get it. Okay, this is a thing what we are proving here. Okay. That's a fixed point. Okay, so let me prove this one. So you put A is equal to F prime of A. Let's put A is equal to, follow this. It's a little, it's not difficult, but it is subtle. You have to understand that there are subtleties in a proof. There are difficulties and major things are used in a proof. So subtle means it doesn't mean that are all complicated. You can even use the elementary stuff to get a proof. But the elementary, you have to use it in a very subtle way, proper way. Then you get the proof. So if you look at it step by step, the proof may not be difficult, but subtleties will be there. So when you read a proof of any theorem, it is important to understand what are the very complicated mathematics is used, and or major theorems are used. That's one aspect. Or very subtle elementary stuffs are used. Elementary stuffs up to that study. I'm not telling that inverse function theorem is elementary for a +1 or +2 students. After learning multivariable calculus, a bit of linear algebra, then the theorem is a kind of an elementary theorem. So given that this is not equal to 0, F prime of A is invertible. That's the given fact, that one. And you given that F prime of X is continuous. F prime is as a map from omega to L of Rn. So I'm using the same notation for F prime and F prime of X. This means that X going to F prime of X is continuous. Okay. Okay. So in particular, continuous at A. Okay. It is continuous, but in particular. So given epsilon, we choose these things again later, smaller. Given epsilon, there exists a neighborhood Later, we may shrink if necessary. You can think as neighborhood as a ball of radius r or some radius. Okay, if you want some convexity and other things. So yeah, I'm not specifying such things so detailed here. If you don't like to write a U in a general neighborhood, it's enough for you to write it as a ball of radius, some radius r. So that's a neighborhood. If you don't like it as a general open set, you take that way. A neighborhood of A. So that's what it says that. So you have an A. Omega is something, so we are not going to do that one. There exists a neighborhood A such that F prime is continuous at A. So I can evaluate, this is the continuity that it's a mapping. Yeah. Hello? Hello? Any question?
It's by mistake someone has unmuted. I'm just muting.
Yeah, I can see that they are looking for, the kid is asking for the dinner, maybe.
Yeah, just 1
That's
minute.
okay, we can understand that at this stage. So, I think. Fine, shall I continue?
Yeah, yes, sir. Yeah.
Okay. So f prime of x, no problem. Such things are fine. F prime of x minus a. This is nothing but your f prime of a. Okay. And this known only thing is eventually you have to understand, right? This is, I don't specify it. This is in 11 of Rn basically. Or the matrix no. So if you are not comfortable yet your L of Rn, sorry. If you are not comfortable with your linear operator theory, etc., just imagine it as matrices. That's why you always try to stay in your comfortable level and try to view instead of going to an uncomfortable position and try to understand things. Stay at your comfortable, but don't stay and sleep there. Stay there and try to move to the other views. Okay, this is less than or equal to epsilon for all x in U. So you got some neighborhood U. So what is our aim? So you keep our aim in between. Okay, let me recall again. We want to solve. So don't forget the aim. Want to solve fx equal to y for y near b. Okay, that's what you have to keep it in mind. Near b. Okay, so you have your x here, a here. A going to b, you know. Our aim is to prove a neighborhood, find a neighborhood. So that for that neighborhood, we may have to shrink this neighborhood later, which you are doing it all the time in math. Why you want to solve for y close to b and some neighborhood you want to solve. So, and this problem, as I said, a problem can convert into a fixed point theorem problems. And there may be different ways of doing fixed point theorem. Certain way of transforming may lead to the contraction, not at every way leading. For example, so this is equivalent to, I can write this equation x equal to x plus I am doing it in a slightly clever way. That's what the whole analysis here. Y minus f of x. Is that convinced? This is your star. This is your double star. I'm solving what star is equivalent to solving double star. That's clear, right? If fx equal to y, this term will become 0, and hence x equal to x is fine, x is a solution. On the other hand, if x is a solution to this one, x and x cancel, and then this term will be 0. And since A inverse is invertible, its kernel is produces 0, and y equal to f of x. So it's nothing but is in the kernel of A inverse. Okay. So even without A inverse, this is a fixed point of this one. The problem is that that fixed point may not work, and this is the right fixed point I need to do eventually and try to analyze that one. So keep this in mind. So the solution of this one, solving this, is equivalent to the solvability. That's what I'm trying to say. It's an equivalent of the solvability. Okay. So I will define phi of x. In case I don't complete the proof, I would like all of you to go through the proof before I want to complete, because again, I don't want to repeat the proof. If you have doubt, I can clear, but in case I don't complete it, I will start where I begin. So you have to go through the proof and come. Phi x equal to, I want to go little slowly because this is the one important theorem we are proving it. A inverse in y minus f of x. Okay. What I said that y fx equal to y, then whatever I said, I am repeating only. Fx equal to y if and only if phi x equal to x. Yeah, that's a trivial thing. So what I'm going to claim now, I want to prove that it is a self-map. Phi is a contraction for phi is a contraction and phi maps some closed board. I today explained to you that one. Still under. In other words, maps, phi maps B for some P bar. It's also a cell map. So B bar is compact. Okay, compact. Which you want to prove it. So here I want to use, though I said there are results like a mean value theorem type. It's something like a mean value theorem type for multi. You have already seen a scalar value function and mean value theorem, which can be used in a similar thing to prove this mean value type theorem, you want to call it, because it's all vectors now. Okay, so what it says that suppose xy belongs to U and norm of so what do I now? Maybe I will write it here. Something here. Suppose if you have a finite norm of in a set f prime of x less than, I have not see Rudin if you want a precise statement. Rudin. F prime of x less than or equal to a uniformly bounded for all x in some set, then you can write it as norm of f prime of x minus f prime of y is less than or equal to. That means if your derivative is uniform, is bounded, then you can write this estimate for all x. So this we use it here now. Okay, so for that I want to compute my f prime of x. Okay, so as a result will be used in that. So what is phi prime of x? I want to compute my phi prime of x. Yeah, you have to get familiarized with that slowly. Your phi x is x. It's an identity map. So you can compute, you can write, look at it if you write down, that's nothing but your identity map, right? Do you understand that one? If phi x equal to x, if fx equal to x, it's a vector identity map, your f prime of x is identity. In terms of Jacobian, you can easily compute it, right? because it's x1, etc. Only the diagonal elements will come with 1. Because only for the first row, you get only dx1 by dx1, 1. The remaining things are 0. That's a one way of actually, it's a crude way of immediately computing. But more than that, it's a linear map. Right? So it's a linear map, its a derivative has to remain similarly. So the f prime acting on any point should give back the same value, okay, as a linear map. So f prime of acting at y will be y. Okay, that's what you have to get that identity. And then look at the second term. Second term, in this term, this part is a constant. Okay, and for this part, it is A inverse f of x. But A inverse is linear operator acting on f of x. So it will only come the derivative of f. If you are not convinced this kind of took argument, you can write down precisely. You write down and compute your f of I prime of x. And that's a nice thing. You are not convinced? Yes, you have to do that one. So this will become minus A inverse f prime of x. Okay, so you have this one, I prime of x. And that can be written as, I will take an A inverse outside, A minus f prime of x. And that will give you my norm of e prime of x is less than or equal to norm of A inverse into norm of A minus f prime of x. Am I right? You make sure that which are all that norm taking. But then we already proved that A minus f of x is less than or equal to epsilon. Here. You see? You see, you have an epsilon there. So this will be less than or equal to epsilon into norm of A inverse. This I call it alpha. Say, call it alpha. So. Okay. So that now apply that result. So you will get it. So epsilon small enough. So you get epsilon small. So you see, epsilon is your choice. So you choose epsilon small so that your alpha is less than half. It doesn't matter how it can be 1/4, something like that. Basically, I want this to be less than 1. So you can choose whatever you want it. You can make it. So that there is nothing sacrosanct about the half there. You will understand that one. Then by that result, no more phi x1 minus phi x2 is less than or equal to, because it's uniformly bounded that derivative, alpha into norm x1 minus x2. That's less than or equal to half, you see. So it's a contraction. So you have to choose that epsilon small, corresponding to that epsilon small, you will get a u. That's how you have to, so each time you have to reset it. Okay, you are basically resetting your epsilon. And when you resetting your epsilon, you are resetting your neighborhood u, making further small u. This immediately implies phi is a 1-1 map. So you got only, you have not yet proved what I wanted really. It's only proved that phi is a 1-1 map. Phi is 1-1. And this is a contraction. No, sorry. Yeah, of course, V is fundamental. You're getting it there. More than that implies phi has at most one fixed point. That's the meaning, right? I'm not talking about that. It cannot have two solutions now. At most one fixed point. You see that immediately? You see that, right? If it has two fixed points, phi x1 equal to x1 and phi x2 equals to x2, then x1 minus x2 will be less than or equal to half into. If you are not understood, just think. There's nothing to think. But still, if you are not taught, think. Okay. So we can have at the most one fixed point. What does that mean? So when it has at most one fixed point, that implies fx equal to y. Fixed point is the solution of this one. Fx equal to y has at most 1x as solution, has at most 1x in U. What does that mean? That implies f is 1, 1 on U. It cannot have two solutions. Since we can have at the most one fixed point, that means equivalent to fx equal to y, given by fx equal to y can have at the most one solution. So f is 1, 1 on U. So put now, so I will, it's already thing. Anyway, I cannot complete what I wanted. Put v is equal to f of u. Then f is mapping from u to v is 1, 1 and on 2. So you have a here. I will ask a question to you, and then you here, B here, you have. Did we prove the first part of the theorem? It's a question. Did we prove the first part of the theorem? Can anybody answer at this late hour? Then I will stop and we'll continue tomorrow. Anyone wants to answer? So you have produced a set U, the domain space. You produced a space V. Of course, V contains B, no doubt, because A goes to B, which is a solution. F of A equal to B. So A is a solution corresponding to B and cannot have one more than that solution. Or you lost the proof. So Soban, students are sleeping, teachers are sleeping.
No, sir. No, sir.
No, sir.
Okay, then tell me the answer. It doesn't matter. You don't worry about wrong answers.
Because
One
of
should be
f of x equal to y onto is clear.
No, what is not clear? That's what my question. Did we prove the first part of theorem?
One I'm thinking because y f of x.
No, assume that 1, 1 is also which is given to you, which I proved. I proved actually 1, 1.
Phi
because phi has at most 1 point, so that if fixed points are equivalent to solutions of fx equal to y.
Okay.
Okay. So phi has only one fixed at the most. I am telling there is a fixed point at the most one fixed point, and fx equal to y has at the most one fixed point. One solution for a given y.
Yes, sir. Then that is clear.
Clear?
Yes, sir.
Anyone wants to support him? What is the condition? You have to. That's why you have to be very carefully read the theorem. Let me go to the. You want to see the conclusion of the theorem? What is the conclusion says you? Read the theorem carefully. You have to show that, shall I tell? You have to prove the existence of open sets.
Yes,
Get the
sir.
point? Eh? Where did I prove V is open? Okay. You need to, that more important part of this result now is the proof of that V is an open set. That's not proved. Then you are done. Claim to prove. You see, subtlety is coming. This is the way sometimes you think that the proof is complete. That's not true. I never said it's a U to V is open. That doesn't mean that a continuous map will lead to open sets to open sets. Please keep that in mind. Okay, that's not as we need not be an open map. It's never done, right? F is only continuous. And that derivative, all that is what is actually showing that it is open. To prove V is open. This is the argument is little more subtle. And we will do it tomorrow. Okay. All right. Okay, then it's time up. I thought I will prove a little more, but needs some 10-15 minutes or maybe. And also you get, so my humble request is understand the theorem very well and come back the half-hour proofs I have done. So it will be easy for me to complete the proof quickly in the 15-20 minutes. And then I can explain to you the implicit function theorem and at least sketch of the proof, and except the last part of the proof, I'll convert that into a problem from inverse function theorem. That much I can do tomorrow. So if you come back with some preparation. Okay. Any more questions? So today working with the 2 laptops, it's worked. I don't know what's still there.
Yes, today there was no problem. Yeah. Are there any questions?
Yeah, are there any questions? Yeah, that can be done. That can be answered.
So we can say the Banach-Fixed-Point theorem has an application in the inverse theorem.
Yeah, we already used a little bit.
Yeah.
We may use it a little bit. We have used extensively that proof of that F is 1, right? U to V is 1, on to. We will use it again, that map phi. We will prove once more, we apply it. That's a little more subtle. With a quick few steps, I would have completed now. But these are all few more steps are there. That is to complete, show that. See, now V is some F of U. You have to take an arbitrary point of V, not just working with B now. You have to take an arbitrary point in V and then show that that's an interior point of V to show that V is an open set. And in other words, you have to show that there is a neighborhood of any, you take any neighborhood of, take any point in V and then take a neighborhood of that and show that every neighborhood in that is solvable back in U, because you want to show that that's an image of F. Then only it will be a neighborhood in V. V contains image points of U under F. Am I right? Yes. So we want to show that V is an interior, V is an open set. You take an arbitrary point, show that there is a small neighborhood, because you have to show that it's an interior point. Showing that it is an interior point, that neighborhood is every point is a image of some point from U. Okay. So
sir, from this calculation, we can conclude the Banach fixed point theorem, the contection mapping is means this is the 1-1, showing the 1-1 also. And from the uniqueness, this is going to the onto.
Onto, because I am taking only the image points. Onto is not coming from that.
No,
I'm
because,
getting 1-1.
because of uniqueness, because we are getting the phi of x equal to.
Yeah, uniqueness is coming, but that's what leads to 1-1ness. Uniqueness is coming to 1-1ness. And then I'm taking V f of u.
Mhm.
Okay, and then f from u to v is onto naturally, because my codomain set is only image set points. That is always the moment you have a 1-1 map, you can take an image, and from the set to that image set will be 1-1 and onto. Any map that is true, right? Suppose if f from x to y, and f is a 1-1 map, then you take f of x, capital X, as some z. Then f from x to z will be 1-1 and onto. That's it. The moment you replace your codomain set by image set, it will get onto this. That's fine. That's not that's a general thing. Nothing to do with any theorem. So that's why you don't get any property of V immediately. Because U is open, the openness is not transferred under continuity. Compactness, these are all topological property there. Okay, so compactness and all that connectedness will transfer to the image, but not openness. So that's why you have a separate definition of an open map. And in function analysis, you would have seen results which gives you open map.
Okay, sir. Thank you.
Any other question?
No, from me, no. Sir.
Yeah. All right. Then if there are no further questions.
Yeah, we can end today's session then if there are no further questions. Thank you, sir. So we will meet again tomorrow at 6. I mean, we will meet you at 7. The session will start at 6. Yeah.
All right.
Yeah.
Is that okay?
Thank you. Yes, sir. Yes.
Yeah.